You think you understand time. You wear a watch. You feel yourself getting older. You remember yesterday, and you plan for tomorrow. Time seems obvious. It seems like the most natural thing in the world. But that's not time. That's just a sensation, a biological trick your brain plays on you. Most people walk around with this poetic idea in their heads that time is a river. You imagine it flows, sweeping you along from the past, through the present, and into the future. You think it moves. But here's the problem with that beautiful image. If time is a river, how fast does the river flow? 1 second per second. That's meaningless. That's like saying a table is 1 table long. It tells you absolutely nothing about the nature of reality. The truth is much stranger, much more mechanical, and honestly, a lot less romantic than a flowing stream. Time doesn't flow. Time doesn't push you anywhere. And if you think you have a good grip on how time works, just because you can count seconds in your head, you're in for a very rude awakening. Let's start with what goes on inside your brain, because that's where the confusion begins. You think your internal clock is a reliable instrument. It isn't. It's a chaotic mess of translation schemes. Consider a simple experiment. Try to count to 60 seconds in your head. Just sit there and count 1, 2, 3. You think you're tracking time, but what you're really doing is running a very specific, very personal program. Some of you, when you count, you hear a voice in your head. You're literally speaking to yourself, sub-vocalizing. 1, 2, 3. If someone interrupts you and asks you to speak, you lose your count. The machine jams. But others, and this is where it gets interesting, don't hear a voice at all. They see images. They might see a tape measure with numbers on it, clicking past like a ticker tape. Click, click, click. If you use that visual tape measure system, you can actually read a newspaper or check a laundry list while you count time. You can sort your socks, look at patterns in the weaving, and still keep that mental tape measure clicking perfectly. But the person who counts with a voice, they can't read a word without losing track of the time. This tells us something fundamental. What you experience as the passage of time is just a mental construct, a pattern-matching game your brain plays. It varies wildly from person to person. It is not a universal constant. It's a biological hallucination. Feynman understood this deeply. He knew that our subjective experience of time, the sensation of flowing from moment to moment, has almost nothing to do with what time actually is in physics. When we talk about physics, when we talk about the universe, we have to throw your brain out the window. We have to stop talking about how it feels and start talking about what it actually is. In physics, we have to be operational. That means we don't ask what is the essence of time, because that's a question for philosophers who enjoy arguing over coffee. We ask, how do we measure it? And the answer is almost disappointingly simple. Time is just a way of ordering events. That's it. It's a labeling system. Imagine you have a deck of cards. You lay them out in a row. You can say the jack is before the queen and the king is after the queen. The cards aren't moving, the table isn't flowing. The order is just a structural property of how the cards are arranged. Time is the table. Events are the cards. When we say time passes, we're just reading the cards from left to right. This brings us to the biggest mistake everyone makes. You think time is a container. You imagine the universe is a big empty box, and time is a clock on the wall of that box, ticking away. Even if the box is empty, you think that if we removed all the stars, all the planets, all the atoms, and all the light, time would keep ticking. Tick, tick, tick. Wrong. This is the Newtonian view, and it's dead. Time is not a background stage. Time is a measure of change. If absolutely nothing in the universe changes, no atoms vibrate, no light moves, no energy shifts, then time stops. It ceases to have meaning. You cannot define a second without a physical process to mark it. A swinging pendulum, a vibrating quartz crystal, a cesium atom oscillating. Time is not separate from the stuff in the universe. Time is a property of the stuff. This is where your intuition fights back. You say, okay, but surely time acts on things. Time makes me get older. Time causes the milk to spoil. No, it doesn't. This is a linguistic trap. Time is not an agent. Time doesn't have hands. It doesn't reach into the fridge and sour your milk. Bacteria do that. Chemical reactions do that. Entropy does that. Time is just the bookkeeping system we use to track the rate at which those reactions happen. Saying time did it is like saying inches built the house. Inches didn't build anything. Carpenters did. Inches just tell you where the walls are. Time is the ruler, not the worker. Feynman was relentless about this distinction. He insisted that in physics, you have to be careful about confusing the map with the territory. Time is the map. The physical processes, the changes, the movements of particles and fields, that's the territory. When you experience time passing, what you're really experiencing is change. You're experiencing your neurons firing in sequence. You're experiencing memories being formed. You're experiencing the metabolic processes in your cells. All of that is physical change. Time is just the coordinate system we use to keep track of when those changes happen relative to each other. Let's push this ruler analogy further, because this is where things get really weird. If time is just a ruler we use to measure the distance between events, what happens if the ruler itself is flexible? This isn't science fiction. This is measurable fact. We used to think that a second was a second anywhere in the universe. If you had a clock on Earth and a clock on Mars, they would tick-tock in perfect unison. It feels obvious, it feels right, and it's completely false. The rate at which clocks tick depends on where they are and how fast they're moving. This is not a mechanical failure of the clock. It is a fundamental feature of reality. Imagine you're driving a car across a giant, flat sheet of paper. You can drive north, or you can drive east. If you drive purely north, you're making maximum progress in the northward direction. But if you turn the steering wheel and start driving northeast, you're sharing your speed. You're moving a bit north and a bit east. You aren't going north as fast as you were before because you diverted some of that motion to the east. Now replace north with time and east with space. This is the essence of relativity. You are always moving through the universe at a constant speed. But that motion is shared between space and time. If you sit perfectly still in your chair, dedicating all your motion to moving through time, you're traveling into the future at maximum speed, 1 second per second. But the moment you stand up and walk or get in a rocket and fly, you're diverting some of that motion into space. You're moving through space, which means you must, mathematically must, move slower through time. Your clock slows down. Your aging slows down. You aren't breaking the machine. You're just changing direction on the map. If you could move at the speed of light, which is the maximum speed limit of the universe, you would be using 100% of your motion for space. You would have zero motion left for time. For a photon of light, time does not pass. It is born and absorbed in the same instant from its own perspective. The universe is frozen. Now you might be thinking, Well, I don't feel my watch slowing down when I run for the bus. Of course not. You're too slow. You're a biological snail. The effects are tiny at human speeds, but they're real. We have to program satellites with this math. GPS satellites are moving fast, so their time is different from your time. We literally have to adjust their clocks. If we didn't, your GPS would be off by miles within a day. This is not theoretical physics. This is engineering. This is practical reality. The fact that your phone can tell you your location to within a few meters depends on understanding that time runs at different rates for satellites in orbit than it does for you on the ground. Feynman loved this kind of thing. He loved that the most abstract, counterintuitive predictions of relativity had become mundane engineering problems. He would point out that GPS is essentially proof that time is not what you experience. Your experience tells you that a second is a second everywhere. But the universe doesn't care about your experience. The universe operates according to its own rules, and those rules say that time is relative. There's another aspect of time that tricks us, and it comes back to that counting problem. The idea of pattern recognition. We perceive time as having a direction, an arrow. Past is fixed, future is open. You can remember breakfast, but you can't remember dinner. Why? If physics equations work forwards and backwards, and most of them do, why can't we remember the future? If you film a planet orbiting a star and play it backward, it looks perfectly fine. It obeys all the laws of gravity. But if you film an egg falling on the floor and breaking, and then play it backward, everyone knows it's fake. The yellow yolk doesn't leap off the floor, assemble itself into a ball, and seal itself inside a shell. Here's the secret. This isn't about time itself. It's about probability. It's about disorder. It is much, much easier to break an egg than to build one. There are a billion ways for an egg to be broken. Scattered here, splattered there, shell in 3 pieces, shell in 1,000 pieces. But there is only one specific arrangement where the egg is whole. So as things move and interact, they naturally stumble from the organized state, few options, to the disorganized state, many options. We call this entropy. And this is the only reason you feel an arrow of time. You're watching the universe shuffle the deck of cards. You started with a perfectly ordered deck, and every second that ticks by is just the universe shuffling it a bit more. You can't unshuffle the deck just by hoping. This means that your sensation of time flowing is actually just your brain registering the increase of messiness in the universe. You're a disorder detector. When you distinguish the past from the future, you're really just distinguishing less messy from more messy. If the universe were in a state of maximum mess, maximum entropy, where everything was evenly spread out and nothing interesting was happening, your brain wouldn't be able to tell the past from the future. There would be no egg to break. There would be no memory to form. In a thermal equilibrium universe, the arrow of time vanishes. Feynman found this fascinating because it means that the arrow of time, the one feature of time that seems most obvious to us, the feeling that time flows from past to future, is not a fundamental property of time at all. It's a consequence of thermodynamics. It's a consequence of the fact that the universe started in a very special, very ordered, very low entropy state at the Big Bang. We don't know why the universe started that way. That's one of the deepest unsolved problems in cosmology. But the fact that it did is what makes our experience of time possible. Without that initial low entropy state, there would be no arrow. There would be no distinction between past and future. There would be no memory, no causation, no evolution, no life. The arrow of time is not a property of time. It's a property of the initial conditions of the universe. So let's go back to those people counting in their heads. The ones seeing the tape, measure, versus the ones hearing the voice. They're both struggling to impose a rigid, linear structure on a universe that is actually much more flexible. We build these mental models, these counting machines, because we need to survive. We need to know when the tiger is coming or when the harvest is ready. We evolved to track duration, but we did not evolve to understand the dimension of time. Our brains are efficient, not accurate. We focus on the now because that's where we live. But in physics, now is a very slippery concept. If you and I are standing next to each other, our now is effectively the same. But if you're on a planet a million light years away and you start walking away from me, your definition of now slices through the universe at a different angle than mine. What you consider to be happening right now might be in my future. What I consider right now might be in your past. There is no universal now that covers the whole universe like a blanket. The universe is a block of events, a four-dimensional loaf of bread, and how you slice that loaf depends on how fast you're moving. This is hard to grasp. It feels wrong. It feels like I'm telling you that up is down. But that's because you're trying to translate the high-level language of the universe into the low-level language of your biology. You're trying to count socks when you should be measuring light beams. Feynman had a way of making this concrete. He would ask you to imagine two events happening far apart in space: a firecracker exploding on Earth and a star flaring up in a distant galaxy. Did they happen at the same time? Your intuition says there should be a definite answer. Either they were simultaneous or they weren't. But relativity says the answer depends on who's asking. For an observer at rest, relative to both events, they might be simultaneous. For an observer moving toward the star flared first. For an observer moving away from the star, the firecracker exploded first. All three. Observers are equally correct. There is no absolute answer to the question of which event happened first. This is not a matter of perspective or opinion. This is geometry. The structure of space-time is such that simultaneity is relative. Events that are simultaneous in one reference frame are not simultaneous in another. And all reference frames are equally valid. There is no privileged frame, no universal clock, no absolute now. When you try to force the universe to fit your intuition, you get confusion. You get paradoxes. But when you let go of what you think time is, when you stop trying to count it like a pile of laundry and start measuring it like a dimension of space, suddenly the equations work. Suddenly the universe makes sense. We're not done, because even if we accept that time is a dimension and that it stretches and squashes with speed, there's a much deeper question lurking at the bottom of the well. We talked about measuring time, and we talked about the arrow of disorder, but we haven't talked about the beginning. If time is a measure of change, what happens when you run the movie backward all the way to the first frame? If the universe is expanding and we wind it back, it gets smaller and smaller, hotter and hotter. Eventually, you hit a point where the laws of physics themselves start to melt. All our clocks, our atoms, our planets, our light beams, they exist inside the universe. But if the universe itself was born in a moment we call the Big Bang, does it make sense to ask what happened before that? This is the ultimate test of your new definition of time. If time is just a way of ordering events inside the universe, then asking what happened before the universe might be as nonsensical as asking what is north of the North Pole. It sounds like a valid question grammatically, but geometrically, it's gibberish. There is no north of the North Pole. There may be no time before time began. And yet, we still have that nagging feeling, that internal counter, that voice counting 1, 2, 3. We desperately want the universe to have a backstory. We want a timeline that stretches back forever. It's hard to accept that the tape measure might just start, that the counting machine had an on switch. This creates a friction between our psychology and our cosmology. We are finite beings trying to comprehend the infinite, using tools made of meat and electricity. It's a wonder we understand anything at all. Feynman was honest about this. He didn't pretend to have all the answers. He didn't claim that physics had solved the mystery of time. He simply pointed out that physics had revealed that time is not what we think it is. And that's progress. That's real progress. Knowing what something isn't is often the first step to understanding what it is. Consider the patterns again. The person who sees the tape measure in their head can count while reading because they're using different circuits, visual versus verbal. Physics is the same. Classical mechanics was the verbal counting. It worked for day-to-day stuff. Relativity is the visual tape measure. It allows us to process complex patterns that the old way couldn't handle. We're constantly upgrading our mental software to match the hardware of reality. And the upgrade process is painful. It requires discarding ideas we love, like the river of time. But here's the beautiful part. Even though your intuition is wrong, even though your internal clock is a biological hack, and even though time is a flexible, relative, bendy dimension rather than a strict metronome, it still works for you. You can still boil an egg. You can still meet a friend for coffee at 2 p.m. The weirdness of relativity is hidden under the hood. You don't need to understand the combustion engine to drive the car, and you don't need to understand space-time metrics to live your life. But isn't it better to know? Isn't it better to know that the engine is there? This brings us back to that strange experiment with the counting. Remember the difference between the person who hears numbers and the person who sees them. This is not just a party trick. It reveals a terrifying gap in how we understand the universe. When two people talk to each other about something complex, like time or relativity or love, they think they're speaking the same language. They nod. They agree. They say, "I understand." But what's really happening? You're running a massive, invisible translation scheme. You take the words I say and convert them into your private internal imagery, which might be completely different from mine. I say 1 minute, and I see a clock face. You hear a voice saying 60 seconds. We arrive at the same answer, so we think we agree. But the machinery inside is totally alien. This matters for physics because it exposes the fragility of common sense. Common sense is just the collection of prejudices you acquired by age 18. It's built on your specific internal imagery. If your mental image of time is a tape with numbers on it, you'll struggle to understand how time can bend. If your mental image is a voice counting, you'll struggle to understand how time can be spatial. When we try to teach you about the quantum vacuum or the curvature of space-time, we aren't just giving you new facts. We're asking you to delete your operating system. We're asking you to throw away the tape measure and silence the voice. And that's why it feels so hard. That's why your brain rejects it. You aren't just learning. You're translating against the grain of your own biology. Feynman understood this better than almost anyone. He knew that teaching physics wasn't just about explaining equations. It was about helping people rebuild their intuitions from the ground up. He knew that you couldn't just tell someone that time is relative. You had to show them why their intuition was wrong. You had to give them new mental tools, new ways of thinking, new images to work with. He spent his whole career developing those tools. The Feynman diagrams, the path integral formulation, the lectures, All of them were attempts to give people a way to think about physics that didn't rely on broken intuitions. And what he found over and over was that when you give people the right tools, when you help them build the right mental models, they can understand things that seem impossible at first. They can grasp relativity. They can grasp quantum mechanics. They can let go of the river and accept the ruler. But it takes work. It takes patience. It takes a willingness to be wrong, to discard cherished beliefs, to accept that the universe is stranger than you imagined. Now let's talk about gravity, because this is where the picture of time gets even stranger. Newton thought that gravity was a force, something that reached across space and pulled on objects. Einstein realized that was wrong. Gravity is not a force. Gravity is curvature. The presence of mass and energy curves space-time. Objects move along the straightest possible paths through that curved space-time. From their own perspective, they're moving in a straight line. It's just that space itself is curved, so their paths look curved when you see them from outside. And here's the part that's going to break your head. Gravity doesn't just curve space, it curves time. In fact, most of what we experience as gravity is curvature of time, not space. When you're standing on the surface of the Earth, you don't feel pulled downward because space is curved. You feel pulled downward because time is running at different rates at different heights. Time runs slower closer to the Earth than farther from the Earth. That difference in the rate of time is what creates what we call gravity. Imagine two twins. One stays on the surface of the Earth. The other lives in a space station, orbiting high above the atmosphere. The twin on the surface experiences stronger gravity, which means time runs slower for him. The twin in orbit experiences less gravity, so time runs faster. After several years, the twin in orbit has aged more than the twin on the surface. The difference is small, only a few milliseconds, but it's real and measurable. We've done this experiment. We've put atomic clocks in airplanes. We've flown them around the world at different altitudes. The clocks at higher altitude, where gravity is weaker, ran faster than the clocks at lower altitude. Exactly by the amount predicted by Einstein's general relativity. Time really does run at different rates, depending on where you are in a gravitational field. This is not a metaphor. It's not an approximation. It's reality. So when you ask what time is in physics, the answer is that time is a dimension of space-time, and space-time is a geometric structure that can be curved by the presence of mass and energy. Time is not absolute. It's not universal. It's not a fixed backdrop against which events unfold. Time is relative, flexible, observer-dependent, and intimately connected to space. Feynman was famous for insisting that physics must be operational. We can't ask what time really is in some deep philosophical sense. We can only ask how we measure it and how it behaves. And what we discover when we ask those questions is that time behaves like a dimension. You can move through space faster or slower. Likewise, you can move through time faster or slower, depending on your speed and the gravitational field you're in. But here's the crucial difference. You can move forward or backward in space. You can go north or south, east or west. But in time, you can only move in one direction, toward the future. Always toward the future, never toward the past. Why? Why does time have this asymmetry when space doesn't? The answer, as we mentioned before, is entropy. The second law of thermodynamics says that entropy, disorder, always increases in a closed system. It never decreases. This is the only law of physics that distinguishes the past from the future. All the other laws are symmetric in time. They work equally well forward as backward. But entropy is different. Entropy has an arrow. It points from low entropy, high organization, toward high entropy, low organization. And that arrow is what creates our sensation of the flow of time. When you see an egg break, you know you're watching the film in the right direction, because entropy is increasing. The organized egg becomes disorganized egg. When you see the film backward and the egg reassembles itself, you know something is wrong because entropy is decreasing, which never happens spontaneously. But here's the deep question. Why did the universe start in a low entropy state? If the Big Bang was an infinitely hot and dense point of energy, that sounds like maximum entropy, maximum disorder. But it wasn't. It was a state of incredibly low entropy. How do we know? Because the universe has been increasing in entropy ever since. If it had started at maximum entropy, there would be nowhere to go. There would be no arrow of time. There would be no change. There would be no structure. There would be no galaxies, stars, planets, life. The fact that we exist means the universe started in an extremely low entropy state, and nobody knows why. This is one of the deepest open questions in all of physics. Why did the initial conditions of the universe have such low entropy? We have no answer. We have some speculations, some ideas, but no tested theory. It might have to do with the nature of gravity. It might have to do with quantum mechanics. It might not even be the right question. But what we know is this. The fact that the universe started in low entropy is what makes time possible. It's what creates the arrow of time. It's what allows interesting things to happen. It's what allows structures to form, patterns to emerge, life to arise. Without that initial asymmetry, without that special low entropy state at the beginning, the universe would just be a uniform soup of particles in thermal equilibrium. Nothing would change. There would be no past or future, just an eternal, boring, unchanging now. So when you ask what time means in physics, part of the answer is that time is the manifestation of the second law of thermodynamics. Time is the direction in which entropy increases. Feynman had a beautiful way of thinking about all this. He said that the laws of physics are like the rules of a chess game. Once you know the rules, you can predict how the pieces will move. But the rules don't tell you why the board was set up the way it was at the start of the game. The initial conditions are separate from the laws. And in the case of the universe, the initial conditions, the low entropy state at the beginning, are as important as the laws themselves. In fact, they're more mysterious because we don't know where they came from. Now, there's another aspect of time that Feynman found fascinating: the relationship between time and quantum mechanics. Classical mechanics, time is just a parameter. It's a variable you plug into your equations. The equations tell you where a particle will be at any given time. It's simple. It's deterministic. It's predictable. But in quantum mechanics, everything is different. In quantum mechanics, particles don't have definite positions until you measure them. Before measurement, they exist in a superposition of all possible states. And time plays a strange role in all this. The evolution of the wave function, the mathematical object that describes a quantum system, is completely deterministic. If you know the wave function at one time, you can calculate the wave function at any other time. But when you make a measurement, something weird happens. The wave function collapses. All those superimposed states collapse down to one. And that collapse process is not deterministic. It's random. It's probabilistic. You can't predict which outcome you'll get. You can only calculate the probabilities of different outcomes. And here's the really strange part. We don't know when the collapse happens. We don't know what counts as a measurement. It's one of the unsolved problems of quantum mechanics. Does the wave function collapse when a photon hits a detector? Or when the signal from the detector reaches a computer? Or when a human looks at the computer? We don't know. Feynman hated this kind of ambiguity. He wanted physics to be clear and precise. And he developed his own way of thinking about quantum mechanics that avoided the collapse problem entirely. It's called the path integral, or the sum over histories formulation. The idea is this. In classical mechanics, a particle takes one path through space. It goes from point A to point B along a specific trajectory. In Feynman's quantum mechanics, the particle takes all possible paths simultaneously. It goes in a straight line. It loops around. It zigzags. It goes backward in time and then forward again. It literally takes every imaginable path from A to B. And each path contributes to the total probability amplitude. The paths add up in a certain way, and some cancel each other out due to quantum interference, and some reinforce each other. And what you get at the end is the probability that the particle ends up at any given location. This is a profoundly strange way to think about reality. It suggests that, in some sense, all possible histories are happening. It's not that the particle is choosing one path, it's that it's taking all paths, and nature is somehow averaging over all of them. And time in this picture is completely symmetric. The paths can go forward in time or backward in time. There's no fundamental difference. The asymmetry, the arrow of time that we experience, comes from somewhere else. It comes from the boundary conditions, from the initial conditions, from the fact that we started in a low entropy state. Feynman found that this way of thinking about quantum mechanics was incredibly powerful. It allowed him to calculate things that were nearly impossible to calculate using standard methods. It allowed him to visualize what was happening in a way that made intuitive sense, or at least as much intuitive sense as anything in quantum mechanics can make. But it also raised profound questions about the nature of time. If particles are really taking paths that go backward in time, what does that mean? Is time really fundamental? Or is it something that emerges from a deeper description? These are questions that still aren't settled, and they bring us to the frontier of modern physics. The search for a quantum theory of gravity, a theory that unifies general relativity and quantum mechanics. In general relativity, space-time is dynamic. It curves and stretches and ripples. In quantum mechanics, everything is probabilistic and subject to the uncertainty principle. Combining these two ideas has proven incredibly difficult. And one of the difficulties is precisely the question of what time is. In some versions of quantum gravity, time disappears entirely at the fundamental level. The universe doesn't evolve, it's just a state, a configuration, a mathematical pattern. What we call time is something that emerges when you zoom out, when you look at larger scales. It's a bit like temperature. Temperature is a concept that only makes sense when you're talking about large collections of particles. A single particle doesn't have temperature. Likewise, time might be a concept that only makes sense when you're talking about macroscopic systems. At the fundamental level, at the Planck scale, the smallest possible scale where quantum gravity becomes important, time might not exist at all. This is a terrifying idea. Your entire experience of reality is structured around time. Past, present, future, cause and effect, memory and anticipation. But physics suggests that all of this might be an illusion, an emergent effect, something that arises from a deeper reality, where time plays no fundamental role. Feynman was careful with this kind of speculation. He always wanted to come back to what we could measure, to what we could test. And what we can measure is that time behaves in certain ways. It slows down when you move fast. It slows down in strong gravitational fields. It's connected to space in ways Newton never imagined. It has an arrow due to entropy. And it plays a strange and not completely understood role in quantum mechanics. Those are facts. Those are things we know. Everything else is speculation. But informed speculation, speculation guided by mathematics and experiments, is how physics progresses. That's how we expand our understanding. And right now, we're in the middle of one of the biggest expansions of our understanding of time that has ever happened. Experiments like LIGO, which detect gravitational waves, ripples in space-time itself, are giving us new windows into how space-time behaves under extreme conditions. Black holes colliding, neutron stars merging, the fabric of space-time vibrating like a bell. These events are showing us the dynamic nature of space-time in ways we could only imagine before. And what we're learning is that space-time is even more flexible, even stranger than Einstein thought. Black holes, for example, have a completely bizarre relationship with time. As you approach the event horizon, the edge of the black hole, time slows down. From the perspective of someone watching you from far away, you take longer and longer to reach the horizon. You never seem to cross it. You look slower and slower, redder and redder, eventually frozen in time. But from your own perspective, you feel nothing special. You just cross the horizon and keep falling toward the center. Time for you runs normally. It's just that for the outside world, you've been frozen. And once you're inside the event horizon, the structure of space-time changes in a profound way. What was the time dimension becomes spatial. What was spatial becomes temporal. You can no longer avoid reaching the center of the black hole, the singularity, any more than you can avoid reaching the next second in your normal life. It's inevitable. The future is literally downward. These aren't metaphors. This is the actual geometry of space-time inside a black hole, as described by Einstein's equations. And it raises mind-bending questions. What happens at the singularity? What does it mean for space-time to become infinitely curved? Do the equations break down? Do we need a new theory? Probably. Probably general relativity is just an approximation. A very good approximation for most situations, but an approximation nonetheless. And in the most extreme places in the universe, black holes, the Big Bang, we need something deeper. We need that quantum theory of gravity we don't have yet. Feynman spent many years of his life working on these problems. He worked on quantum gravity. He worked on cosmology. He worked on the foundations of quantum mechanics. And always with that same attitude. No pretensions, no mysticism, just physics, just equations, just measurements. Just trying to understand how things really work, not how we want them to work, not how it would be romantic for them to work, but how they really work. And what he found, again and again, is that reality is stranger than fiction would dare to imagine. Time is not what it seems. It doesn't flow. It's not universal. It's not absolute. It's relative, flexible, intertwined with space, influenced by gravity, marked by entropy, and possibly not even fundamental. And yet, here you are, reading these words, feeling time pass, feeling yourself age, feeling yourself move from past to future. That feeling is real. It's part of your experience, but it's not a reliable guide to how the universe works. The lesson of Feynman, the lesson of all modern physics, is that you have to let go of your intuitions. You have to let go of what you think you know. You have to be willing to accept that the universe is profoundly different from what it seems. And when you do that, when you let go of the comfort of your expectations, what you get in return is something far more valuable. You get the truth. You get a real understanding of how nature works. You get the power to make predictions, to build technology, to manipulate the world. You get the ability to send signals across continents in milliseconds, to navigate the world with meter precision using satellites in orbit, to build computers that can process billions of operations per second. All of that requires understanding time. It requires understanding relativity. It requires letting go of the idea of time as a river and accepting time as a dimension. So what does time mean in physics? It means this. Time is a coordinate, a dimension of four-dimensional space-time. It's relative, depending on your state of motion and the gravitational field you're in. It's flexible, stretching, and contracting according to the presence of mass and energy. It has an arrow, defined by the increase of entropy, pointing from the ordered past toward the disordered future. It's inseparable from space, bound to it in a unified structure that can curve, ripple, and vibrate. And possibly, it's not fundamental, emerging from a deeper quantum reality where time as we know it doesn't exist at all. That's what time means in physics. It's not a simple answer. It's not a comforting answer. But it's the truth as we currently understand it. And it's far, far stranger and more beautiful than any river you could imagine. Feynman would say that you shouldn't feel bad that your intuition about time is wrong. Everyone is born with the same wrong intuitions. They evolved to keep us alive on the African savanna, not to understand the structure of space-time. The miracle is that humans, using nothing more than mathematics and experiments, have been able to discover the true nature of time. That we've been able to go beyond our intuitions, beyond our common sense, and find the real laws that govern reality. That's a triumph of human intellect. That's what makes physics beautiful. Not that it tells us what we want to hear, but that it tells us what is true. And the truth about time is that it's a dimension, not a river. It's a measure, not an agent. It's relative, not absolute. And it's deeply, wonderfully, inexplicably strange. So the next time you look at your watch, remember, you're not seeing time. You're seeing a device that counts oscillations of a quartz crystal. Time itself is something far deeper, far more subtle, and far stranger than that little device on your wrist could ever suggest. This is what Feynman taught us. This is what physics reveals. Time is not what we experience. Time is what we measure. And what we measure is far stranger than what we feel.